So the clock is very misplaced because we can't see it. So actually yesterday you totally caught me off guard when you said it was time. Yeah, I think it would be great to actually put it on that chair. It doesn't matter. Oh, yeah, absolutely. Yes. Sorry, you can definitely have this seat because I won't be sitting down. I just need a space for my water. And maybe I can also put that. No, I have a desk here. So.
Thank you.
Sorry.
That's fine. Yeah. Oh, he moved to your place already. Talking about you. I was 2 seats next to you. Oh, you were.
Okay. Can you hear me in the back? Yep. All right. Great. So let's get started for the second lecture. So let me just very briefly recap where we left it off yesterday, and I hope that we'll get through the Generalized Symmetry 101 introduction today, and then get to more geometric engineering questions next time. So two references, there'll be some things where I'll just say, you can check this, you can look it up. There are these ICTP lecture notes. They're mostly non-invertible, but there's one section that's invertible that'll be relevant for this. So that's something maybe you can look into. And then also recently there were these notes by Brennan and Hong. All of these are very recent. So there isn't really a complete review of invertible, generalized symmetries yet. But I think these might be very useful. Okay, so we started off talking about Noether and how we think about zero-form symmetries, so standard global symmetries in terms of topological defects. And the point we were making yesterday is we should think of zero-form symmetries as being generated by codimension 1 topological operators. So I will always denote them by capital D sub the dimension of the operator. And then here it'll have a group label G, and G is valued in this flavor symmetry or global symmetry. This can be a continuous symmetry, but it can also, in this abstract sort of way, be a discrete symmetry, like charge conjugation or whatever comes to your mind as a discrete symmetry of a quantum field theory. Then we extended this to p-form symmetries, and there we just say, well, we can change the dimension of these operators. So here they were codimension 1, here they're codimension p plus 1. Again, now G is a group, and as someone rightfully pointed out, because now in D dimensions, these topological defects, we can move them past each other in space-time, they have to be abelian. Otherwise, we get something inconsistent. Okay, so these codimension p plus 1 operators generate the p-form symmetry, and the charges are p-dimensional defects. So just like for zero-form symmetries, they were acting on local operators, so zero-dimensional operators. P-form symmetries act on p-dimensional operators, and they will transform in some representation of this group GP. And the way to see that this is the correct dimensionality is, again, by linking argument, which is something I told you you could look into as an exercise when you have a current formulation. Okay, so one other alternative, are there actually questions about this? So far, so good. Okay, good. So one way of thinking about these sort of higher form symmetries, in particular one-form symmetries, that'll be useful later in these geometric considerations, is to not focus so much on these topological defects, but actually formulate this more in terms of these charged objects. So actually an alternative perspective say on one-form symmetries, but you can generalize it to p-form symmetries. Let me focus on one-form symmetries, is the following. So let's consider a gauge theory and let's say we know all its line operators. Let's call L the set of all W1 alpha line operators. So for example, you're in an SU2 gauge theory and you write down all the possible Wilson line operators. Then I can define on this set L so an equivalence relation. So two line operators, let's call them W1 and W1 prime, they're equivalent if and only if there exists a local operator O, so that I can write them as there's W1, O, W1 prime. So there's a junction between these two line operators formed by this local operator. So then I call these two line operators to be equivalent. If I now actually look at the set L modulo this equivalence relation, this will be, so what I call the set of charges. And in fact, these charges will be precisely the dual, or the Pontryagin dual, to what we call the one-form symmetry group. So one way to understand this is, if I have a one-form symmetry, I have these codimension 2 topological defects from here. And now I can measure the charge by linking them with these line operators, right? And essentially, if I have local operators, right, I didn't say that W1 or W1 prime can't be trivial, right? If, say, for example, this line operator can end, let me write this down as, won't use this. So for example, if W1 can end on a local operator, I can think of this as the sort of W1 prime, which is just a trivial line operator. Then actually this topological defect, and I need my color again, I think green. So I can sort of link with the D2G. This is the one-form symmetry generator, right? And I can ask, can I actually, so the charge should be now this linking. I can calculate it here, but if in fact I can sort of end this operator, I can also take this to this side here, and then collapse it, and here I would get the charge is actually of this line operator is 0, right? So in fact, in this case, you would say a line operator that ends, or is a junction, there's a junction to the trivial Wilson line, in fact, screens this one-form symmetry. So in this sense, this equivalence relation sort of accounts for these type of lines that can end, okay? So the charges are basically all the different line operators modulo these junctions that that theory can have. So actually, let's look at an example, because it's quite So an abstract construction. Let's look at an SU2 pure Young-Mills theory. Let's do it in 4 dimensions, but we can do it in really any dimension. So what kind of line operators do we have? We have Wilson line operators. And Wilson lines essentially are, just in some representation R. So this is a rep of the algebra SU2 and some path. So let's call it again M1. So this is some path-ordered exponential trace in the representation of A. So what kind of Wilson lines do we have in a pure gauge theory in 4 dimensions? All right, so you should think of this Wilson line as sort of an infinitely massive particle, a probe particle, and its world line. So what kind of line operators do we have in a pure SU2 gauge theory? What representations? Yep. Right, so there for SU2, we have so spins J equals to 0, half, 1, and so on, right? And now, when I actually look at this whole set, with all of these J's, so this R is basically labeled by J, so the set L that we had is all these WRJs. And now the equivalence relation says, whenever I have local operators that form these kind of junctions, then identify these Wilson lines. So what kind of O's, what kind of O0s do I have in a pure gauge theory? The representations of, so the O's, zeros in a pure gauge theory with gauge group SU2 are basically in the adjoint representation. Right, they're like F and tensor products. So to some n. So they'll be actually the sort of integral spin one. So I've got 1 and so on and so forth. So in fact, I can form now a junction. If I have this Wilson line, and I have the Wilson line with in R with J equals to 1, there's now a local operator O. I can end that. Right? Whereas the Wilson line with W R J equals to 1/2, I can't end. Yes? Because there's no representation. I didn't put any fundamental matter in my theory. So in fact, in this case, I measure this, I can trivialize it. In this case, I can't trivialize it, so this is actually a non-trivial charge. And there's, of course, also the trivial Wilson line, which is just, so you can't see the bottom of this. Let me erase this like this. So W R J equals to 0. So these two are the independent ones, and this gets screened. Right? And so this, in this sense here, the charges form a set Z2. So this L modular equivalence relation is Z2. And in that sense, this is what I would call charges, which is then the dual. So these are the representation of this one-form symmetry group, which in this case is Z2. So L mod twiddle being Z2 means that the group G1 is Z2, because these are essentially just the representations of it. And the dual group of a finite abelian group, cyclic group, is again the group itself. So this is how we see in gauge theories what the one-form symmetry or its charges are. So more generally, we can now say, well, if we added, actually, are there questions about this? Yep.
So we also consider the the same mechanism, right, to screen all of the FF lines?
Yeah, so here I spoke specifically about SU2 group. So I will actually get to the full lattice of all lines, Toft lines and Wilson lines in a moment. Yes, absolutely, for sure, yes. Any other questions? So if we add it now, j equals to 1/2 matter. So we have some SU2 plus some number of fundamentals. Then, in fact, by this sort of argument, this line here, Wj equals to 1/2, also gets now screened. And so Z2 is completely broken to nothing, actually the trivial group 1. Okay? Now there's, of course, also the set of sort of magnetic charges. And in fact, we should discuss this a little bit more carefully. Here I picked from the beginning an SU2 group. Now, if I just give you a gauge algebra, that's maybe not necessarily what you actually should be considering. So if you actually start with a bit more abstractly consider some G Lie algebra. And let's take it to be of ADE type. So everything is simply laced. All the roots are square to 2. Then, in fact, we can have line operators. That are either Wilson lines, so they are labeled by weights. And these are the Wilson lines. Or we can also have Toft lines, and they're actually labeled by the magnetic weight lattice. And these are the Toft lines. So when we have this is sort of the full superset of possible line operators, when I haven't specified yet any kind of group, gauge group that I'm considering. But if you actually look at these, there's some redundancy. So in fact, indeed, if I have the weight lattice, so this is basically all the weight, so this is really the weight lattice. And the magnetic, the dual weight lattice, so the magnetic. Then there's some redundancy because indeed, if I have a pure gauge theory, I can always screen with something that's in the adjoint. So in fact, I should mod out by the roots. So lambda roots, this is the root lattice. And for ADE, that's the same. This is also the dual, so the co-root lattice. Then all the possible line operators are in fact lambda W mod roots plus lambda magnetic weight mod roots. Yeah? So before, you're just looking at this here and saying that's what we have for the SU2 gauge theory. Now, what is the problem with looking at this full set of, let's call this curly L, line operators? If I consider the theory with, and I have some gauge algebra and I pick W, magnetic W's, and I just stick in all these line operators into the theory, there's a problem with this. You can't have sort of Wilson lines and Toft lines at the same time in, say, in here, for example. Well, what is the problem? So these are Wilson, and these are Toft lines. So the issue is that these are not so take an arbitrary line L with some lambda and weight, so electric and magnetic charge, and some lambda, some mu electric, mu magnetic, and I move them around each other and exchange them, they will actually pick up a phase, which is sort of given in terms of this pairing of these two, maybe 2 pi, two charges, so these two charge vectors. Right? I pick an arbitrary weight in here, an arbitrary magnetic weight, and look at some line operator with lambda and another one with mu and exchange them. These are not mutually local. Where here, this is this Dirac pairing.
What do you mean by exchange then?
If I put them in a correlation function, who asked this question? You. Right? If I actually put them in a correlation function, I can ask, is it, and these are lines in 4 dimensions, so I can definitely move them around each other. And I can ask, is this sort of the same as having them before? Are they actually mutually local operators in your space-time? And it shouldn't depend on how I've calculated this, right? I can move them around and pick up this phase. So in fact, I should consider only line operators where this phase is trivial. Because otherwise, whenever I place these two lines in my space-time, it will depend on how I've placed them in there.
Sorry, so you have the 2 lines, like the 2 sides of this equality?
Yeah.
The lines here and then...
I can, move them around. It doesn't, it's like if I have an electric and magnetic particle, you have this phase that you pick up, this standard Dirac argument. And so this is exactly the same effect here. And this pairing here is also exactly this pairing between electric and magnetic charges. So this is given in terms of, so this lambda mu is just lambda e mu m minus lambda m mu e. So in fact, I should only be looking at configurations where this is actually integral. Only such things we should really call theories which have a consistent set of line operators. And
Sorry, can you say again, what's the inconsistency of the not a true phase?
that it was?
What is the inconsistent?
Oh, yeah, I will repeat it again. So if you have, say, the argument is very similar to if an electron monopole, and now you look at sort of the wave function of, say, one in the presence of the other. And as you sort of move this around, you pick up a phase, right? Because this creates a field, and this monopole picks up a phase. And now, of course, it shouldn't depend. This is the Dirac string argument. This should not depend on, that how this phase should be absent, right? And that sort of gives you a quantization condition of the electric and magnetic charges in a quantum field theory. And here, this is exactly the same argument. So here we should have, so mutually local set of lines, we require that the charges are integral, and in fact, we can call sort of a subset lambda inside L is a polarization which translates into a consistent global form of the gauge group is a polarization if it is is a maximal mutually local set. Operators. So one polarization that we discussed just there was, so an example, so if lambda is just purely electric, so you only have Wilson lines, that's obviously consistent with the integrality. And this actually for SUN, let's say we're looking at SUN, gauge algebras, then this corresponds to precisely the SUN, now capital SUN gauge group. Yeah. And we have all the representations, and again, the one-form symmetry in this case is just given in terms of the center. So this quotient there, there's an exercise in the Lie algebra theory, which I didn't mention there, but I should. And these quotients, of course, can be computed for an arbitrary Lie algebra, and they're given in terms of the center of G. So for SUN, the center is precisely Zn. So these are all the elements that commute with everything in G. Okay, so here we have Zn, and this is so what you call a Zn one-form symmetry. That's an electric version because we have just these weights and no magnetic weights. But of course, we have another obvious choice, which is just picking the magnetic. And these are sort of just Toft lines. And this becomes the PSUN. So in this case, the PSUN gauge group, which has again a Zn one-form symmetry, but now magnetic. And these are not, of course, the only choices. If n is, say, has a non-trivial divisor, you could also consider other subsets. So in fact, you can think of the PSUN, and we'll discuss this in a moment, as gauging this SUN, gauging sort of the center of the SUN to go to PSUN. You can gauge different subgroups as well. That's right, yes, I'll write this down in a moment. So where's the dry erase? Oh, thank you. There's exactly one left. So I need to save this. So PSUN is basically SUN or the quotient by the center. But what basically this magnetic one-form symmetry is the non-trivial pi1 of PSUN. This is basically the Zn magnetic one-form symmetry in that case. So if we go back to this SU2 example, that's maybe the most instructive to look at here. How would we get the SU2 mod Z2 case? Let's actually look at this again. So the SU2 mod Z2, also known as SO3, yes, please ask the question. It doesn't have to be. It's just when it's not simply laced, you need to worry a little bit more about the co-roots and all this. I just want to not go into that. But absolutely, you can also look at SP and other groups for sure. It's just to simplify this particular piece of the argument. Okay, so let's recap these. So we have, for SU2, we said we have basically Wilson lines, the trivial one. So J goes to 0, and W1, J goes to 1/2. For the SO3, in this case, we have, in fact, so this corresponds to choosing just lambda e comma 0. That's our polarization. So all these is the electric polarization. So SO3 will be the magnetic ones. And we can go from here to here by gauging now Z2. And what exactly is now the difference between usually SU2 and SO3? Well, here there's this non-trivial class that actually Nadi was talking about yesterday. There's a W2, so there's an obstruction to lifting. The gauge configurations to SU2, which is also spin 3. Right, so normally we would just write for SO3 the simply connected version as spin 3. And so this W2 is essentially, so we'll see later on, to go from here to here, you essentially sum over these configurations W2. Okay, so this is sort of the story of one-form symmetries and for a generic gauge group. And I would like you to think about it either in terms of simply the center, and why is it the center? It's essentially coming from this picture of there can be local operators that screen these line operators and in that way trivialize part of the sort of set of all lines. And the other important point is you cannot just pick any arbitrary subset of lines. You actually need to require there to be a polarization. Okay, so are there questions about one-form symmetries? Yes?
What's the simplest way to screen the
So you can add monopoles, right? So in the same way you would add here, and for SU2, right, you would add fundamental matter. Here you would add monopoles. Any other questions? Yep.
So coming from like a quantum gravity perspective, the maximality requirement of the polarization makes sense. But just from like a QFT perspective, what's the motivation for requiring maximality of the polarization?
Okay, so in some way, right? So for example, okay, it's a good question. And you could also consider, say, a subset of Wilson lines, but in fact, if I sort of take tensor products of them, I would presumably generate. So for example, if I had some fundamental and I just picked sort of some subset of the weights, I can sort of generate the remaining ones.
SU4 and you only take like the even charge matter.
Yes, but then I think you would still, so what you're doing at that point, you have looked at this, right? But then you actually have a dual symmetry. So you would have here sort of a Z2 electric, but also a Z21 magnetic that you to generate after you've gauged the Z2. I don't think this answers your question, but this is. I think the statement is this is sort of the set of the maximal set you can have. You cannot take more than these. So you sort of, it gives you the set of possible line operators you can have in that set, in that theory, and then the associated one-form symmetry, rather than so that you need to have this complete set in a given theory. Okay, so another very important point is to discuss actually for these higher form symmetries background fields. So one thing we will get from these string theory constructions is, and also that will be important in holographic constructions, is a formulation of these symmetries in terms of these background fields. And of course, we know how to couple zero-form symmetries to backgrounds. Also, Nadi was discussing this today and yesterday. So background fields for p-form symmetry groups. So we will assume it's an abelian group, because so we don't necessarily need to repeat the story for G0. But if you actually start with G0 and couple this to a background, the G0 background field a zero-form symmetry so you all know how to do this for continuous symmetry. If actually G0 is finite, and that's the case we'll need to discuss for these p-form symmetries, zero-form symmetry that is a finite group, is essentially associating this background field A1 associates to a one cycle, a flat, so it's a flat gauge field, and associates to an M1. An element little g in G0. So we can also write this sort of in terms of, we have some holonomy, so e to the I integral A1 will be some element in G0 over this M1 cycle. So for example, this we can do for, if this is Zn, then we would associate a group element in Zn, just a phase, to a one cycle in our space-time. And we can sort of write this as, so I will not have time to discuss what is cohomology with finite group coefficients, but this is what the meaning of the following sort of thing is. So we have our space-time MD, and this is the meaning of this cohomology group. So in fact, dA is 0, and we associate to one cycles some holonomy in Zn. One way you can realize this is in the case for Zn. It's nice because you can embed this also into U1. So for more general groups, this won't be possible, but for Zn, you can embed it into U1 and actually write sort of these background fields also as U1 fields, and we can sometimes do this. In the same way now, the higher form symmetries we can couple to background fields by associating an element in GP to a cycle which is P plus one dimensional. So for GP, so again, it's morphic to some Zn, a background field will be a field B, P plus 1, NH, P plus 1. And all this means is it's flat and assigns a G in Zn to a p+1 cycle in your spacetime. So a nice exercise actually is, so see this for continuous p-form symmetries. You can sort of do the standard thing by essentially adding to your action now some, so for your QFT, you add some I integral bp+1 star of some current b minus p for this higher form symmetry. And so then you can actually see or convince yourself that this is indeed the correct sort of structure. You should actually have a background field for p-form symmetry is a p+1 form. In this continuum way, you can just apply what you know for a standard zero-form symmetry. For these discrete symmetries that we'll be interested in, we'll just essentially generalize this argument of a flat gauge field as associates group element to one cycles. Okay, yep. Sorry?
Is the counting right? Doesn't that one add to p+1?
Sorry? Oh, here? Okay, -1. Right, so, sorry, so we have star, okay, so let's do the calculation. So star of this will be a p-form, and I think you are right. So this actually, the whole thing is d minus p minus 1. How about that? Okay, thanks. Okay, so actually, I'll tell you here. Okay. So when we have these background fields, we can also ask, well, we can gauge usually zero-form symmetries by now summing over background or integrating, path integrating over these background field configurations. How does this work for p-form symmetries? And that works sort of in this discrete world as we're summing now over all possible values for this bp+1. So let's just discuss this briefly here. So there's some gauging a p-form symmetry will result in a dual G hat. And now you need to put the hats in the correct place, as is a dual symmetry, which is a G d minus p minus 2 form symmetry. So here we had a background field bp+1, and on this side we have a background field which is a d minus p minus 1. So for example, for the case of a U1 field, this is just basic gauging in the usual sense, but now in this discrete world, right? So this is actually, as before, an element of our GP. So this is some usually finite group. So if you have a partition function for our theory, we can couple this. So this is our QFT. and we couple it to a background field, BP plus 1, we can in fact gauge GP by summing over all BP plus 1. So I guess there's now sort of a finite set of elements, so GP. So the theory T mod GP will now have this dual field, and that's up to some normalization that I won't discuss. The sum over all these BP plus 1 with some weight factor of the partition function coupled to this background field BP plus 1. And so what actually this is sort of a weight factor. You can think of B and B hat essentially like you're doing a discrete sort of Fourier transform. And this is sort of your e to the IXP. And one question, of course, is why is this a well-defined thing? And what is this pairing on B and B hat? And that's sort of naturally given by the following argument. So this pairing is now pairing of HP plus 1 with GP values times this dual field. So this is D minus P minus 1 forms with values in this G hat, D minus P minus 2. And the claim is this goes to essentially R mod Z. So the first observation is, well, in terms of forms, P plus 1, I can dualize these forms. I can use Poincaré duality and map this HD minus P minus 1 to HP plus 1. And now I can take this P plus 1 form and integrate this, or pair it with this P plus 1 cycle. And so now I can sort of integrate this HP plus 1 form over this HP plus 1 cycles. Integrate is really not the right word here, but let me just leave it. If you know the more refined statement, you know what this means, and if not, then this is a good way of thinking about it. And now also, these groups are not actually the same groups. So what actually is G hat of D minus P minus 2? That's in fact precisely the Pontryagin dual so this means it's just the Homs from GP into U1. So this is exactly what I was saying earlier. Here, for an abelian group, this is essentially the characters of this group, and that's given in terms of this dual group G hat. So again, this makes sense. This gives us a U1 phase. And so this pairing is sort of sensible in that sense. So this is what this pairing is. And now, with these sort of background fields in place, I can answer one of the questions I think that came up yesterday. How do you write down these generators of higher form symmetries when you don't have currents? Right? So in our Noether procedure, we actually could write down the actual charge, the current, the charge, and this D sub d minus 1 operator. So in fact, with these background fields, we can write down the generators of both the GP and its dual G hat D minus P minus 2. And namely, these are given in terms of, so for the P-form symmetry, these need to be D minus P minus 1 dimensional defects. And those are precisely the backgrounds for this dual symmetry. So let's call this here, these of some manifold M, D minus P minus 1. They're just the holonomous integral of this B hat. And this is for GP. And for G hat, these are now P plus 1. And then e to the I, some parameter if you want, alpha. And these sort of operators actually, even if you've not worked with higher form symmetries, will be quite familiar. Even they sort of show up even in very simple sort of setups, like if you're looking at higher form symmetries and looking at topological operators in say BF theories. Yeah. This is just saying if I have a theory, it has it shouldn't have a Toft anomaly, so I can gauge the symmetry. It's a global symmetry. I can gauge the symmetry. So if this is a continuous symmetry, you know what to do, right? You write down path integral, some of all the gauge configurations. When this is sort of a finite group symmetry, I need to tell you what replaces this integral, right? And what replaces the integral is now a sum over all these BP plus 1 in HP plus 1. Yes? And then this is, if I have a theory with that symmetry, it's non-anomalous, I can gauge the symmetry, and the partition function of that new theory, it will have, so here this is sort of a coupling to the background gauge field for this dual symmetry, but this is now a theory where I've gauged the GP symmetry, it'll have this partition function. For B equals to 0. Oh, yes, right. So for P equals to 0, if you have in abelian groups, that's why I said I restrict here to abelian groups, right? Everything about continuous groups, non-abelian groups, and you have some global symmetry, you want to gauge it, you know what to do, right? You did your QFT course. For discrete symmetries, finite discrete symmetries, you do not. And that's what the case I actually discussed here. So even for finite zero form symmetry, you would do exactly the same thing. So it's like a restriction of the continuum picture where you integrate over continuous gauge configurations now to these finite gauge configurations. Yeah?
What if I have a discrete non-abelian zero form symmetry? Because then I don't have this nice.
Yes. Yes. Then I will relegate this question to the fourth lecture when we talk about the SymTFT, because then I don't need to talk about any of these things, and I just say there are topological defects in my bulk topological field theory. I just pick boundary conditions. So indeed, so there's an important restriction here. The zero form symmetries can also be discrete but non-abelian, like for example permutation groups, and you can gauge these symmetries. And then of course this doesn't quite work, but there's still a way to formulate such things, which hopefully I can get. And it actually relates also to this comment here. These topological defects here, these ones here, You can think of them as the topological defects of a BF theory. And this is sort of comment in anticipation that I probably may not quite get there, because I was supposed to be here about 24 hours ago, so slightly delayed. So these d minus p minus 1 and dp plus 1 are in fact the topological defects of a now d plus 1 dimensional BF theory. So yeah, I'm assuming there are no Toft anomalies. These are completely just these topological defects are in the theory. So namely, these are sort of, they live in some md plus 1, where I have these background fields dp plus 1, which, okay, let's not do, if you have to write down the cup product, I will just write it down in terms of, let's say if it's a Zn symmetry, it's the b minus p minus 1, okay? Yeah. So this is a BF theory. It's called BF because B and then the field string F, or Dijkgraaf-Witten theory, for fields which are Zn fields because of this n, so the EOM, so these are n times dB is 0, so these are flat, but actually torsion fields. And in fact, these are precisely the topological defects of that theory. And that's actually not a coincidence at all, because this is what much later on you may think of in terms of the theory that governs sort of all of the symmetry structures of that theory. One other comment is, these, of course, these type of couplings you've seen in other contexts too. So this is sort of, for example, if you now have a 4-dimensional theory, QFT, and you have a one-form symmetry, then this would look like n integral b2 d, let's put a hat here, d hat 2. And this BF coupling is, of course, a coupling you've seen, for example, in there's a 5-dimensional coupling that appears also in holography. And in holography, this is exactly sort of, if you're looking at A is 5 times is 5, this is n is the SUN n, B2 is the NSNS B2, B2 hat is the RR2 form, and this coupling, constructing those topological defects, and then suitably choosing boundary conditions for them, meaning these polarizations will precisely give you global forms of the dual CFT. This is a very side remark, but this is sort of how you should think about these types of topological defects and topological operators. Okay. And yeah, one more comment. These will, of course, link with the p-dimensional operators, and these with the dual operators for the dual symmetry. Okay, are there questions about these background fields and also these defects that you can construct from these symmetry generators? Yep.
Is there a way to write down the defects for symmetries that have Toft anomalies?
Yes. And in fact, okay. So for example, we can see, this is a little bit of a side remark. So this was a side remark, this is a side remark. So for example, in this case here, this is a one-form symmetry, a 4-dimensional theory. This could have a Toft anomaly with a 0-form symmetry, like in n equals 1 pure Young-Mills theory. So for example, there could be an additional coupling which is the background field for a discrete zero-form symmetry, and then B2 squared. It's a 5-dimensional topological coupling. So now you can ask, well, what are the analogs of these operators now in a theory where I have these additional couplings? And in fact, right, so essentially what will happen is that you will have to dress the defects. So there's now, of course, there's a zero-form symmetry. So if I actually write down the full, zero form is dual to, this one-form field is dual to a C3, so there's an A1, the C3 type coupling. Right, there's a zero form and a two-form dual symmetry. Well, in fact, this C3 will actually be dressed by this B2 squared. So the topological defect for this zero-form symmetry will now be dressed by this anomaly. And once you then impose suitable boundary conditions, you get non-invertible symmetries. So I think you will discuss that in week 3 or something. So absolutely, you can write down these type of couplings. So the BF theory is sort of the vanilla one-form symmetry, dual one-form symmetry generators, but with anomalies, you will get potentially defects that don't just have group-like composition. Sorry? So I think basically because of these pairings that are now erased, right? So if you do B goes to D lambda, B plus D lambda, they will just be killed in the sum. Yeah. Any other questions? Okay, so the last sort of thing I would like to discuss, which is probably just about right for half an hour, is so we've looked at higher form symmetries. Theory can have zero form, one form, two form symmetries. Usually, if you have sort of a collection, you can also, of course, have a minus one form symmetry, but let's not consider that. So you have zero form until D minus one form symmetries. You can ask, do they actually just form sort of a product group? Is that the symmetry group? Or is it actually something more complicated, like there's some interrelation between, in particular, these topological defects? And so if the symmetry is not a product of the GQ, but what I'll define in a moment an extension, then we'll call this a higher group symmetry. And if I have, say, just a G0 and G1, then it can form a higher group, which is a two-group. Or more generally, if I have P, then there's a P plus 1 group symmetry. And I'll now explain what exactly that is and how we detect these things, because that'll be what we'll discuss then also in these 5-dimensional theories. So what does it mean for a zero form and a one form symmetry to actually have an extension? Well, it might be useful to first look at what an extension group is for zero form symmetries.
P form symmetry, do you have to have a GP minus, like GP minus?
No, you don't. No. You can also just have, a zero form and a two form symmetry and a 5-dimensional. Yes, you can then write down an extension of these two as well. So we'll discuss 0 and 1 form to a 2 group, but let's actually sort of small recap of what actually is an extension in even just looking at the 0 form finite symmetry. And the classic example of an extension is you have something that contains some G, where I can embed, so these are group homomorphisms, so here I can embed a Z2, and when I take the quotient, I also get a Z2. Right, so this is an embedding, and this is a quotient. So usually this is like a short exact sequence of groups, but the question is how many different choices of this G do I have for finite groups G, such that this is a consistent setup. This is well known, of course, but what is one possibility? The obvious of G can be which groups? Thank you. And how are they characterized? Who said this? Of. Right. And that happens to be Z2. And that exactly tells us how many different extensions of this type do we have. And these are really the two. This is the Klein-4 group, this is the cyclic group, and they are not isomorphic groups. So this is what you could call a zero form symmetry extension, right? So if there's now this non-trivial class, then in fact you go to the Z4, and your zero form symmetry isn't just the product of the two Z2s. And the way you should think about a higher group symmetry is along the same lines, when actually one of these will be a one form symmetry, and in some suitable sense, the other one is a zero form symmetry. Okay, so more generally, if there's an abelian group, if these are all abelian groups, this is the group cohomology that classifies the types of extension. And we have a similar group, or there's some cohomology group for the types of two groups, which we'll discuss. Okay, so higher groups, so two groups. So in a very crude approximation, there are extensions of a one form symmetry and a zero form symmetry. But we need to specify a little bit in what sense that is sort of the case. And the hallmark of a two group is, so these B2 background fields we said in this vanilla one form symmetry setup, they were all closed. But in fact, we'll say that actually B2 is not closed. So in fact, B2, this background field, has a variation. So delta B2 or dB2, in fact, is non-zero and is a function of the one form symmetry, the zero form symmetry background. So there are two types of two groups. So there's one which I'll call sort of a split two group. And in this case, we have, say, a one form symmetry group. And there's a zero form, a finite zero form symmetry that acts on this one form symmetry. So an example that's very useful to keep in mind for this is, consider a spin for n, pure Yang-Mills theory. What is the center of this? So the center Z of this is Z2 times Z2. So if you look at the Lincoln diagram, essentially there's a spinner and a co-spinner, and both of these sort of generate, so the one-form symmetry for this group is the center, which is just Z2 times Z2, and this is the spinner and the co-spinner line. And the zero-form symmetry is now just the exchange of these. So this is G0. So G0 is Z2, and it exchanges the spinner and co-spinner Wilson lines. And it's an outer automorphism of spin for n. So now what we'd like to do is write down what does this mean in terms of the background fields. So if I actually call the background field B2 for the one-form symmetry, and now G0 will be some E1, and B2 basically can now be in one of these two Z2s. So let's say one is the S, and the other one is B2C. And then there's a diagonal, which is D2V, which is just S times C. Then there's a non-trivial relation that says that the delta, the variation of this B2 for V, is actually A1 B2C. And that's sort of saying, as I pass through this codimension 1 defect, in fact, I sort of, with codimension 2 defect, I actually sort of emit, pass through with this the B2V, for example, I emit a B2C. So it's sort of like this kind of picture. This is our D3 zero form, and as I pass through with a D2 for V, I actually basically have S and C. So the zero form guy acts non-trivially on these, on the V and the C and the S topological defects. But that's not the kind of two group I actually want to focus on. There's a slightly more subtle version of a two group, which is called a two group with Postnikov class. And that's what will happen as a symmetry of these 5-dimensional gauge theories, or SCFTs. And for this, we have to actually study a little bit more the slightly more mathematically challenging. So we'll need to have a little bit more understanding of these different cohomology classes. So the second type of two group again, they have some relation that this is non-zero, but this is now given in terms of some 3 form that we'll specify in a moment. Before I actually discuss this slightly more elaborate mathematical framework, let me give you an example how you should think about these types of two groups. Yep. Oh, I see. Okay. 2 minutes, really? Okay, I was somehow working to the 12:15. Okay, great. So let's exactly. So this is what we need. So we said a one-form symmetry. I can also think in terms of, so this is the dual group, but for these finite groups, these are isomorphic. I have Wilson lines with some equivalence relation given by local operators. what these types of two groups are is this local operator can be also charged under flavor symmetry. Right, some good old continuous flavor symmetry. Say if I look at a gauge theory, so for example, the simplest example where this happens is for n plus 2. One form symmetry is Z4 in this case. And I add to it some 2.5 times some vector matter. So I have a flavor symmetry, and these types of local operators that screen now are also charged under that zero form flavor symmetry. So if I actually couple this not just to background fields, if I actually couple this to background fields for this flavor symmetry, I can also discuss not just gauge Wilson lines, but also flavor Wilson lines. And those flavor Wilson lines, if I keep track of them, essentially now I can refine this relation and say, well, let's consider line operators. So actual gauge, so Wilson lines, say, comma, flavor Wilson lines, and some equivalence relation on the set, where this equivalence relation, so let's call them W and F. So W and F is the same, is equivalent to W prime F prime if there is now sort of, this is W prime, and if I now just keep track of this local operator, that'll tell me the one form symmetry. But now I'm also keeping track of the flavor symmetry. So I now have these flavor Wilson lines. So in fact, I also keep track. So now this local operator transforms both in some gauge representation, R, but also R for the flavor symmetry. So if there exists such an operator, such that I can write down such a junction. So this is essentially, and I take this set and I quotient by this relation, that'll be the analog of that Z4. And I'll discuss this for about 10 minutes on Thursday. And then I really need to get going with some more string theoretic things. But are there any questions about this so far? Yeah? Yeah, so then in fact you actually have an S3, and so you can gauge the full S3, and then that's actually very interesting to study, what kind of symmetries you get, and they're actually non-invertible symmetries. Yeah?
So also in this example, could we say that B2 is closed, but with respect to some twisted codifferential?
Yeah, absolutely. That's why these are a little bit, they're more like, there are still two groups, but they're mathematicians might even say they're just trivial in that sense. They're just twisted cocycles. Whereas those ones, let me just write down one more thing, if Oliver allows me to. Here, if we so there's some flavor symmetry group, and now this sort of important point that Nadia was making is that we are interested in really the symmetry groups that act faithfully. So here, faithful actually means this is the flavor symmetry group, not just some simply connected thing that we think is maybe the symmetry, but actually the one that acts faithfully. Then this class is in fact in some H3 of BF okay. So this is in delta B2. I'll explain this about W2, where this W2 is now in the H upper 2 B of this flavor symmetry with C, where C is essentially this one form symmetry for these Wilson lines. But I will explain that next time. Yes? You have a question? No? Okay, because you did this. Okay, any other questions? No? Okay, so
Thanks, Sakura. See you all back at 2 o'clock.
no? No? So actually not. So here this is the weight level, modulo the weight level, that's the center. Right? So totally related. However, now the actually taken lines are we may not be
Yeah, do you want to just take a picture of it?
Yeah. Oh, delta, that's different. Oh, I thought it's like this variation on the. It's the exterior delta.
Thanks. I got it.
I left and I'm basically figured out straightforward that generalization. Like, is the polarization the same regardless?
Because actually, if you're doing it, not as three-dimensional